Boötes Void is a region of space where space seems to be devoid of its usual structure, where chains of galaxies usually stretch, forming filaments and clusters. There is an almost absolute void. But this emptiness is not simple. It preserves traces of ancient processes, invisible forces, and rare islands of matter. Deep in the dark fabric of the universe, there is a gigantic region stretching for hundreds of millions of light years, where the density of galaxies tends to a minimum. This is not just a rarefied space, it is one of the largest failures in the cosmic structure. The boundaries of this region are outlined by thin threads of galactic clusters, like a shell holding an inner void. Inside this region, the usual web is missing, the same cosmic network consisting of dark matter and baryonic matter where galaxies form. Here, gravitational nodes are extremely rare, and the density of matter is so low that the processes of galaxy formation are almost stopped. Space is stretched, expansion is accelerated, and gravity is unable to assemble matter into large structures.
However, complete emptiness is an illusion. Inside, however, individual galaxies have been discovered. They are rare, isolated, and often different from those found in dense clusters. These galaxies evolve in conditions of almost complete solitude. Their evolution proceeds slowly, without frequent collisions, without gravitational perturbations of neighbors. They retain ancient characteristics, as if frozen in time. Such galaxies often contain large amounts of gas and show weak star formation activity. In the absence of external pressure and interactions, the processes inside them proceed differently. The spiral structures may be less pronounced, and the nuclei may be less active. These are a kind of archives of the early universe, where you can observe what galaxies looked like before the cosmic web became dense and complex. The reason for the existence of such giant voids is related to primary density fluctuations in the early universe. In the first moments after the expansion, areas with slightly higher and slightly lower densities appeared.
Over time, gravity intensified these differences. Dense regions became even denser, forming clusters and superclusters, and rarefied regions became increasingly empty. This is how giant voids appeared. Cosmic voids. Boötes Void is one of the most extreme examples of such a process. It is approximately 330 million light years in diameter. This means that light will take hundreds of millions of years to cross it completely. In comparison, typical voids are much smaller. The same area stands out for its scale and sharpness of borders. The gravitational dynamics inside the void are different from dense regions. It is not gravity that dominates here, but the stretching of space. Matter gradually flows towards the boundaries, increasing the contrast between the void and the surrounding structures. This process continues for billions of years, making the void more pronounced.
Interestingly, powerful clusters of galaxies form at the boundaries of the void. These structures look like walls or shells surrounding empty space. They are made up of thousands of galaxies bound by gravity and serve as a kind of void boundary. These walls are part of the cosmic web where threads of dark matter intersect. Dark matter is still present inside the void, but its density is much lower. This affects galaxy formation. Without a sufficient gravitational framework, gas cannot contract efficiently, and star formation remains weak. Thus, the void is not just the absence of galaxies, but a region with unique physics. Studies of such areas allow us to understand exactly how the large-scale structure of the universe was formed.
The voids serve as natural laboratories where the effects of dark energy, the force that accelerates the expansion of space, can be studied. Inside voids, this effect is especially pronounced since the gravitational resistance is minimal.
Galaxies inside this void sometimes exhibit unusual properties. Some of them have a high proportion of gas and low-mass stars. This indicates a slow evolution. Others may be dwarf galaxies, barely visible against the background of outer space. Their faint glow makes them difficult to detect. The absence of frequent collisions means that such galaxies are rarely subjected to strong gravitational perturbations. In dense regions, galaxies often interact, merge, and change shape. Here, they remain stable for billions of years. This makes them unique objects for studying the primary conditions of formation. However, even in the void, rare interactions are possible. Sometimes, two galaxies can come closer, causing a burst of star formation. Such events are extremely rare, but they create a contrast between calm and sudden activity.
The boundaries of emptiness play an important role in the dynamics of matter. Gravitational forces at these boundaries attract matter, forming dense structures. This creates the effect of pushing matter out of the center of emptiness. As a result, the central areas become even more sparse. On the scale of the universe, such voids occupy a significant proportion of the volume. Although galaxies and clusters attract attention, most of the space is in such sparse regions. This means that emptiness is not an exception, but an important part of the cosmic structure. Light passing through such a region practically does not interact with matter. This makes observations difficult, but at the same time makes it possible to study background objects without strong distortion. Voids become a kind of windows to the distant universe. Some hypotheses suggest that such voids may affect the distribution of the cosmic microwave background. Due to differences in gravitational potential, photons can experience small changes in energy as they pass through such regions. This phenomenon is known as the integral Sachs-Wolf effect.
The void of Boötes remains the object of active research. Its structure, origin, and impact on the environment continue to be studied. The new observations make it possible to detect fainter galaxies inside it, gradually filling in the picture. Still, even with the new data, this area remains one of the most mysterious. Its scale and sparsity raise questions about the initial conditions of the universe and the role of dark energy in the formation of such structures. Emptiness is not absolute. It is filled with thin streams of gas, rare particles, and a weak gravitational background. But compared to dense regions, this is almost nothing. It is this contrast that makes it so unusual. The galaxies that exist inside continue to evolve slowly, isolated from outside influences. Their light, overcoming hundreds of millions of light years, carries information about the processes taking place in conditions of almost complete loneliness.
This is how the picture is formed. A gigantic region surrounded by dense structures, inside which rare islands of matter are hidden. A space where gravity is weakened and expansion is intensified. A region that demonstrates how the universe can be not only saturated, but also almost empty. It is in such places that it becomes clear that the cosmos is not only luminous clusters and bright galaxies, but also vast, silent regions where the structure almost disappears. Boötes Void is one of the most striking examples of this hidden side of the universe. The inner region of the Boötes Void is not static. Even with extremely low density of matter, there continues a slow redistribution of matter.
These currents stretch the space even more, increasing the contrast between the void and the surrounding structures. Rare galaxies inside a void often exhibit an abnormally high proportion of neutral hydrogen. This gas remains unused because there are no external triggers capable of triggering intense star formation. In dense regions, such triggers arise due to collisions and gravitational disturbances, but here, these processes are almost absent. As a result, galaxies can conserve their gas reserves for vast periods of time. Some of these systems have extremely low metallicity. This means that they contain few heavy elements formed in the interior of stars. This chemical composition indicates a limited number of star formation cycles and supernovae. These galaxies seem to reflect earlier stages of the evolution of the universe, when heavy elements had not yet accumulated time.
The shape of galaxies inside the void is also different. Irregular and weakly expressed structures are often found. Spiral arms, if any, can be less dense and less clear. The disk structures are preserved, but their dynamics differ due to the lack of external pressure. In some cases, dwarf galaxies with a chaotic distribution of stars and gas are observed. Gravitational interactions within the void are extremely rare, but not completely excluded. When such events do occur, they become significant for the local environment. Even a faint approach can cause gas redistribution and a short-term spike in activity. These rare episodes create local contrasts in an otherwise calm environment. The boundaries of the void continue to accumulate matter. Galaxies at these boundaries form extended structures, walls and filaments. These structures are part of a larger cosmic network where dark matter flows intersect. In such nodes, massive clusters are formed, containing thousands of galaxies, hot gas, and powerful gravitational fields. The shape of galaxies inside the void is also different. Irregular and weakly expressed structures are often found. Spiral arms, if any, can be less dense and less clear. The disk structures are preserved, but their dynamics differ due to the lack of external pressure. In some cases, dwarf galaxies with a chaotic distribution of stars and gas are observed. Gravitational interactions within the void are extremely rare, but not completely excluded. When such events do occur, they become significant for the local environment. Even a faint approach can cause gas redistribution and a short-term spike in activity. These rare episodes create local contrasts in an otherwise calm environment. The boundaries of the void continue to accumulate matter. Galaxies at these boundaries form extended structures, walls and filaments. These structures are part of a larger cosmic network where dark matter flows intersect. In such nodes, massive clusters are formed, containing thousands of galaxies, hot gas, and powerful gravitational fields.
The transition from emptiness to dense structure occurs gradually. There is no sharp boundary. The density of matter increases as you get closer to the walls. This gradient reflects the dynamics of expansion and gravitational attraction acting simultaneously. The internal regions push matter outwards, and the external structures hold it. The influence of dark energy in such regions becomes especially noticeable. As gravity is weakened, the accelerated expansion of space manifests itself more strongly. This makes voids key objects for studying cosmological acceleration. Their geometry and evolution may contain information about the properties of dark energy. Light passing through the void experiences minimal gravitational lensing.
This allows you to observe more distant objects with less distortion. However, at the same time, this reduces the likelihood of detecting weak structures inside the void itself, since there are no effects that amplify the signal.
The temperature of the intergalactic medium inside the void is lower than in dense regions. The hot gas characteristic of galaxy clusters is almost absent here. Instead, cold and rarefied gas, which is extremely unevenly distributed, predominates. This affects the cooling and compression processes necessary for the formation of new stars. An interesting feature is the kinematics of galaxies inside the void. Their velocities relative to the center of the void are often directed outwards. This is due to the fact that matter gradually leaves to denser regions. This effect creates an additional expansion within the void, increasing its sparseness. Some observations point to the existence of many structures inside the void, weak filaments and tiny groups of galaxies. These structures are extremely difficult to detect, but they confirm that even in the most empty regions of space, residual organization of matter is preserved. These many structures may be remnants of the original density fluctuations.
Over time, the void continues to grow. As the universe expands and the contrast between dense and sparse regions increases, such regions become even more pronounced. This means that in the future, voids will occupy an even larger share of the volume of space. The evolution of galaxies inside the void follows a unique scenario. Without external influences, their development is determined by internal processes: gravity, gas dynamics, and stellar evolution. This creates conditions for the formation of stable but slowly changing systems. The light from such galaxies carries information about the rare environment in which they exist. Its spectrum can show the peculiarities of the chemical composition, temperature, and density of the gas. This data helps to reconstruct the conditions inside the void and understand how they differ from denser regions.
On the scale of the cosmic web, such voids play the role of the opposite of nodes and threads. They form structure due to their lack of density, creating the contrast necessary to form the complex geometry of the universe. Within this geometry, the voids connect with each other, forming vast regions of rarefied space. These areas can merge, expand, and change shape. The Boötes Void is one of the most striking examples of such a process, demonstrating how primordial fluctuations can lead to the formation of giant empty regions. Even in conditions of near total emptiness, fundamental forces continue to operate. Gravity, dark energy, and the dynamics of space-time shape the evolution of this region. Their interaction creates a complex but barely noticeable picture, hidden behind a seeming emptiness.
Thus, this region remains not just the absence of galaxies, but an active part of the cosmic structure. Its study reveals processes that cannot be observed in denser regions. The void becomes the key to understanding how the universe forms and evolves on the largest scales. Deeper within the void of Boötes, an even more subtle picture of the distribution of matter emerges. At first glance, the space appears uniformly empty, but a detailed analysis reveals faint density gradients that are almost imperceptible. These differences determine the trajectories of rare galaxies and gas flows. Even minimal deviations in density intensify over time, forming barely noticeable directions of movement of matter. Internal flows are directed to the periphery, but their speed is low. They are stretched over millions of light years and create little to no turbulence. This movement can be described as a slow flow of matter towards the boundaries. As a result,
the central areas become increasingly rarefied, and the contrast between the center and the edges increases.
In such conditions, dark energy plays an important role. It is this that determines the accelerated expansion of space inside the void. In the absence of significant gravitational attraction, this effect becomes dominant. Space expands faster than in dense regions, where gravity partially restrains this process. Because of this, the distances between rare galaxies inside the voids are increasing faster than the average for the universe. This leads to the gradual isolation of these systems. As time passes, they become less and less connected to each other, losing even weak gravitational interactions. Light passing through such areas can experience changes in energy. This is due to the effects that occur when passing through a changing gravitational potential. One such phenomenon is the Sachs-Wolf effect, in which photons from the cosmic microwave background gain or lose energy. Inside voids, this effect can create faint temperature anomalies against the background of CMB radiation.
Rare galaxies inside a void can have unusual rotation dynamics. Due to weak external influences, their disks remain stable, and the orbital velocities of stars reflect the distribution of dark matter within the galaxies themselves. This makes them important objects for studying internal structure without external distortions. Some of these galaxies exhibit an asymmetric distribution of gas. This may be the result of weak flows passing through the void or residual formation effects. Such features make it possible to trace the history of the movement of matter, even under conditions of almost complete isolation. Inside the void, there may also be extremely weak radio signals coming from rare sources. These signals are difficult to detect, but they can contain information about magnetic fields and the intergalactic medium.
Magnetic fields in such regions are probably weaker than in dense structures, but do not disappear completely. Powerful processes are observed at the boundaries of the void. Where matter accumulates, shock waves and hot gas are formed. These areas can radiate in the X-ray range, creating a sharp contrast to the cold and dark interior. The transition between these modes reflects fundamental differences in density and temperature. Sometimes chains of dwarf galaxies are found inside the void, lined up along weak filaments of dark matter. These structures are so sparse that it is difficult to distinguish them against the background of the general distribution. However, they confirm that even in the most empty regions, a trace of the space network remains. Over the course of cosmic time, such voids can merge with each other. As adjacent sparse regions expand, their boundaries intersect, forming even larger voids. This process leads to the enlargement of the structure of the universe, where voids become the dominant element.
The evolution of such regions is closely related to the initial conditions set in the early universe. The small density fluctuations that occurred in the first moments intensified over time, forming both dense clusters and voids. The Boötes Void is the result of just such an amplification, an area where the density was initially below average. Inside the void, there are practically no powerful sources of radiation. This makes it one of the quietest regions of space. There are no bright active cores, no intense bursts of star formation. Everything happens slowly and almost imperceptibly. Yet even in this silence, evolution continues. The gas gradually cools, stars age, galaxies slowly change. These processes are stretched over billions of years and proceed without external interference. The gravitational potentials inside the void are extremely small, but they still form the structure of motion.
Even weak gravity can determine the orbits inside galaxies and the direction of gas flows. This creates a complex, albeit weak, dynamic picture.
On the scale of the entire universe, such voids play a key role in the formation of large-scale structure. They determine where the dense regions will be located and how matter will be distributed. Without them, the cosmic network would not have its characteristic cellular shape. Thus, inside this gigantic region, there is not just a void, but a whole system of slow processes, weak interactions, and rare structures. All of this creates a unique environment that is different from any other region of space. And the deeper we look at this area, the clearer it becomes that even where there is almost nothing, the movement, evolution, and interaction of fundamental forces continue. Emptiness turns out to be not an absence, but a special state of cosmic matter and space, where the laws of the universe manifest themselves in their purest form.
Further delving into the structure of the void Boötes reveals even more subtle features of the distribution of matter and energy. In the central regions, the density reaches values close to the minimum possible within the large-scale structure of the universe. Here, even rare gas particles are separated by huge distances, and interactions between them occur extremely rarely. This sparseness affects the state of the intergalactic medium. The gas in these areas is not subjected to significant heating, since there are no powerful sources of energy. As a result, it retains a low temperature and can remain in an almost undisturbed state for billions of years. This makes the inner regions of the void a kind of reservoirs of primary matter, preserved without significant changes. Within these spaces, the influence of cosmic expansion in its purest form is manifested. Without significant gravitational resistance, distances between objects increase faster than in high-density regions. This leads to a gradual erosion of even those rare structures that are still present.
Galaxies closer to the center of the void experience minimal external influence. Their evolution is determined exclusively by internal processes. Stars in them form slowly, and gas is consumed extremely economically. This creates conditions under which such systems can exist much longer than their counterparts in dense regions. Particular attention is drawn to weak gravitational fluctuations within the void. Despite their small size, they can affect the movement of matter on an enormous scale. These fluctuations form subtle waves of density that propagate through space and gradually change the distribution of matter. The interaction between dark matter and baryonic matter manifests itself differently here. At low density, gravitational potentials become smoother, without sharp differences. This causes the structure of the void to appear more homogeneous, even though it actually contains many weak inhomogeneities.
On the periphery of the void, the active accumulation of matter continues. Galaxies, moving from the inner region, gradually join denser structures. This process resembles a slow outflow of matter, reinforcing the emptiness from within, and at the same time, strengthening its boundaries. An important aspect is the effect of the void on the propagation of radiation. Photons passing through such regions practically do not collide with matter. This makes voids transparent to different radiation ranges. However, changes in gravitational potential can still affect their energy and trajectory. One of the manifestations of such effects is the connection with relic radiation. Voids can leave faint traces in its structure, creating temperature anomalies. These anomalies help to reconstruct the distribution of large voids and their impact on the evolution of the universe.
The inner regions of the void may contain extremely faint traces of ancient processes. These traces are preserved due to the absence of intense interactions that could destroy them. Thus, the void becomes a kind of archive where the early stages of the formation of the structure of the universe are recorded. Some models suggest that inside such voids there may be super rarefied streams of gas connecting rare galaxies. These streams are virtually invisible, but can play a role in transporting matter and energy over vast distances. Their existence remains the subject of active research. Over time, the boundaries of emptiness become more and more clear. The contrast between the inner and outer areas is intensified, creating a more pronounced structure. This is because matter continues to move towards dense regions, leaving the central regions increasingly empty.
Galaxies at the boundary are affected by both emptiness and dense structures. This makes them transitional objects in which a mixture of effects can be observed. Their properties can differ from galaxies both inside voids and in dense clusters. On the scale of space, such voids form a complex network of interconnected regions. They are not completely isolated, but are connected to other voids through weak structures. This network defines the geometry of the universe on the largest scales. The evolution of the cosmic web is closely related to the development of voids. As dense regions become more massive, the voids expand, taking up more and more space. This leads to the fact that the structure of the universe is becoming more and more contrasting. Even in conditions of extreme rarefaction, fundamental laws continue to apply. Gravity, the expansion of space, and the interaction of particles form a dynamic that, although almost imperceptible, remains continuous. Inside this silence lies a complex system of processes stretched over vast periods of time. There are no rapid changes here, but it is the slow processes that determine long-term evolution. And the deeper this area is analyzed, the more obvious it becomes that emptiness is not the absence of structure, but its special form. It reflects the balance between the forces that shape the universe and demonstrates how even minimal differences in density can lead to the formation of gigantic spaces where almost nothing is there, but still continues to move and change. The final picture of Void's Boötes is revealed not through vivid events, but through almost imperceptible changes stretched over cosmic epochs. This region does not reach a state of complete immobility. On the contrary, it is here that the continuity of the evolution of space is most clearly manifested. The inner regions continue to lose matter, the boundaries become denser, and the distinction between almost empty and saturated is intensified to the limit. Over time, rare galaxies inside the void find themselves farther and farther apart. Their weak gravitational bond gradually weakens, and each of them becomes more and more locked in its own dynamics. The gas is slowly depleted, star formation dies down, and the light becomes weaker. These systems go into a state of long, steady evolution without external impulses. Flows of matter, barely discernible in the present, continue to move towards the boundaries. This process does not stop. Even minimal gravitational differences direct matter outward. The boundaries of the void thicken, turning into even more pronounced structures, while the central regions become more and more rarefied. The influence of dark energy in such an environment becomes decisive. The expansion of space gradually dominates any residual forces of attraction.
This leads to the fact that the void is not just preserved, it is intensified, enlarged, and consolidates its existence as a stable element of cosmic architecture. Over time, mergers of neighboring voids are possible. The boundaries between them are blurred, forming even larger areas of rarefied space. In such a scenario, Boötes Void becomes part of an even larger structure where emptiness becomes dominant. Light passing through this region in the distant future will carry fewer and fewer traces of interaction. Space is becoming more transparent, and any signals are becoming weaker. However, it is this transparency that makes such regions unique. They preserve the purity of cosmic processes that are not distorted by dense matter.
Against the background of this evolution, a deep connection with the cosmic web is manifested. Voids are inextricably linked with threads and knots, forming a single system. Their growth and development determine the shape of the entire structure of the universe. Without voids, there would be no boundaries, no contrast, no geometry of the cosmic web. Eventually, the inner region of the void approaches a state of extreme sparseness. There are only rare particles, weak fields, and isolated galaxies that exist in conditions of almost complete absence of external influence. But even in this state, the movement continues. Slow, almost imperceptible, but inevitable. This region does not disappear or fill up. It becomes an increasingly pronounced part of the cosmos. Its existence confirms that the structure of the universe is determined not only by where there is matter, but also by where there is almost none. Emptiness shapes shape in the same way that density does.
And in this deep, cold rarefaction, a fundamental pattern emerges. Even where the density tends to zero, the universe continues to evolve. Space expands, energy is distributed, structures are slowly transformed. Nothing freezes completely. Boötes Void remains a symbol of this dynamic, a gigantic region where absence becomes form and sparseness becomes the key to understanding the entire cosmic structure. There are no bright boundaries and abrupt events, but there is an ongoing process that lasts billions of years and determines the future distribution of matter. This is how the picture ends, not as an end, but as a continuation of an endless change. Emptiness is not the final stage, it is only one of the forms of existence of the universe, where the laws manifest themselves in their purest, most unaltered form, and where even the almost complete absence becomes part of the great structure of the cosmos.